Good afternoon, everyone. May I request everyone to be settled? We may start the program in the next 2 to 3 minutes. Good afternoon, ladies and gentlemen. We are delighted to welcome you all to the landmark event, the 21st Foundation Day Lecture of MGMI. On the behalf of MGMI, I welcome all dignitaries, distinguished guests, and esteemed members of MGMI. To begin our proceedings, I request our esteemed dignitaries to kindly grace the stage. Our President, Shri Satish Jha, Secretary Dr. Chandrasekhar Singh, and our guest speaker, Shri Padma Shri Dr. K. Balasubramanian. On the behalf of MGMI, I welcome you all again to this landmark event, the 21st Foundation Day Lecture of MGMI. We shall now mark the formal commencement of this program with the lighting of lamp. May I request our dignitaries on the stage to join us for the ceremonial lighting of the lamp, symbolizing the quest for knowledge and the light of innovation. Thank you, sir. As we celebrate our 21st Foundation Day lecture today, it is worth remembering the MGMI roots go back to 1906. For over a century, this institute has been the backbone of India's mineral policy and a global pioneer in mining and metallurgical sciences. Now, it's my honor to invite Sri Satish Jha, President MGMI, to the podium to deliver the welcome address.
Respected Chief Guest Padma Shri Dr. K. Balasubramanian, distinguished dignitaries on the dais and off the dais, esteemed members of the MGMI, ladies and gentlemen. On behalf of the Mining, Geological and Metallurgical Institute of India, I extend a very warm welcome to all of you to this 21st Foundation Day lecture. MGMI, established on 16th January 1906, is one of the oldest professional institutes in Asia dedicated to the advancement of mining, geology, and metallurgy. Since its inception, the institute has been committed to promoting the study of mineral resources and mining methods, and to disseminate the knowledge for the economic development of the mineral industry in India. Over the past century, MGMI has played a pivotal role in fostering knowledge exchange, professional excellence, and industry collaboration through technical lectures, seminars, conferences, and publications. It continues to serve as a vital platform bringing together industry leaders, academicians, researchers, and policymakers to shape the future of the mineral sector. As we move towards celebrating 120 years of MGMI in 2026, we have already stepped in the 121st year. We reaffirm our commitment to supporting innovation, sustainability, and responsible resource development in the mining and allied sectors. It is indeed a matter of great pride for us to have with us today Padma Shri Dr. K. Balasubramanian, a distinguished scientist and director of NFTDC, whose contributions to advanced materials, critical minerals, and national technology missions have significantly strengthened India's scientific and industrial capabilities. We are honored by your presence, sir, and look forward to your insightful address. I once again welcome all of you and wish you an enriching and meaningful session. Thank you. Thank you very much.
Thank you, sir. We are privileged to have a truly distinguished personality with us today. Now I request Sri Satish Jha sir to kindly felicitate our guest speaker, Padma Shri Dr. K. Balasubramaniam, with a bouquet as a token of deep respect and appreciation. Thank you, sir. Moving ahead, may I invite the Secretary of MGMI, Dr. Chandrasekhar Singh, to formally introduce our guest speaker to this August gathering.
Good afternoon. Respected chief guest of today's event, Dr. Bala, respected President MGMI, all the dignitaries of the dais, the council members, and all the esteemed members of MGMI, all the members who have joined through online streaming, watching this event. On this special occasion of the 21st Foundation Day lecture of MGMI, it is my privilege to introduce our distinguished guest speaker, Padma Shri Dr. Krishnamurthy Balasubramanian, fondly known as Dr. Bala. Dr. Balasubramanian graduated from IIT Kanpur with distinction in BTech Metallurgical Engineering in 1982. He was awarded the prestigious Alkan Fellowship and pursued direct PhD at McMaster University, Canada, specializing in thermodynamics of materials, thermokinetics of processes, process development, and optimization. During his doctoral work, he also served as a teaching faculty at the Department of Material Sciences and Engineering. In 1990, Dr. Bala returned to India to take up the challenge of establishing Non-Ferrous Materials Technology Development Center, we know today as NFTDC, in Hyderabad. Over the last 35 years, he has transformed NFTDC into a unique, self-financed R&D institution that bridges the gap between research, product development, and commercialization. He envisioned and implemented a mission mode approach, integrating materials, processes, products, and manufacturing system, including indigenous equipment development. This has created a self-sustaining technology model in the high technology sector, making NFTDC one of its kind in India. Under his leadership, NFTDC has evolved into multidisciplinary technology center, working across TRL 3 to TRL 8, combining scientific knowledge, that is know why, and engineering capability, that is know how. The institution brings together expertise in material science, mechanical designing, electronics, instrumentation, and system integration. Dr. Bala has established several centers of excellence, including those for advanced material and critical minerals under NCMM, engineering design and manufacturing, electrical vehicle technology, biomedical devices, and material and energy system. His contributions have supported major national missions, including Chandrayaan, Mangalyaan, and Gaganyaan, particularly in development of cryogenic engine materials. His team has also delivered significant achievements such as advanced knee prosthesis with clinical trials, fusion reactor component for ITER, and India's first rare earth magnet plant commissioned in 25-26 with an industry partner. Currently, he is leading national programs in critical materials, hydrogen systems, and electric mobility, and is driving separation technologies and pilot to commercial scale plants for recovery of key minerals, including rare earth elements, lithium, niobium, tungsten, moly, nickel, cobalt, zirconium, hafnium, and vanadium. Dr. Bala is widely recognized for pioneering the material plus process plus product plus plant system approach, executed in a mission mode across multiple sectors. He has conferred the Distinguished Scientist grade in 2012, one of the youngest to receive this honor. He has mentored numerous researchers and guided PhDs across interdisciplinary domains such as material science, process engineering, pattern recognition, knowledge management, and biomedical applications. His many awards include the Young Metallurgist Award, Vasvik Industrial Research Award, Citation of Merit in Biomedical Devices, and Best Scientist Award in Non-Ferrous Material Technologies. He currently serves as an expert member of the Technology Advisory Group to Principal Scientific Advisor to the Government of India and contributes to the national initiatives including Rare Earth Mission Corridors. Above all, Dr. Balasubramanian is an institution builder who has demonstrated a next generation model of technology enterprise, contributing significantly to India's goal of self-reliance, that is Atmanirbharta. In recognition of his outstanding contribution to science and engineering, he has been conferred the prestigious Padma Shri in 2026. A big round of applause, ladies and gentlemen. As MGMI celebrates its rich legacy, continued commitment to advancing the mineral and metallurgical sectors, it is most fitting that we are guided today by such an eminent scientist and advisory leader. In this context, I would like to conclude with a timeless Sanskrit shloka, that is Vidya Dadati Vinayam, Vinyadayati Patratam, Patratatva Dhanmapnoti, Dhanat Dharma Tatha Sukham. Means knowledge imparts humility. From humility comes worthiness. From worthiness, one earns prosperity. From prosperity comes righteousness. And from righteousness, a true happiness is attained. This beautifully reflects the journey of a true scholar and leader, one who transforms knowledge into service for society. An ideal that Dr. Subramanian's life and work so profoundly embodies. Ladies and gentlemen, it is my proud privilege to invite Padma Shri Dr. K. Balasubramanian to deliver 21st Foundation Day lecture of MGMI. Sir, we are deeply honored by your presence and kindly request you to address the gathering.
Can you project, sir? Namaskar. Good afternoon, everybody. When Dr. Singh was telling me about this foundation lecture, it was actually for January 15th or 16th time. And I said, no problem. It's all, Sankranti is over and some good things will happen. That's the saying, right? So, yes, and they have come down a few times to our place. So thank you very much, sir, for inviting us. And Mr. Jha was also here in the dais. And I, being in non-ferrous, we all think that anything other than iron and steel is fine. So coal is also fine, I thought. So that's how I came in contact with them. With critical minerals being in the air and talk, everybody was saying that please talk about our critical minerals thing. So we came up with a roadmap and solutions for the next 5 years for the country. And I thought I can spend some time on that today. So thank you very much. And I see a lot of Bhishmacharyas in the dais, people who have spent half a century probably plus, in the field and still being active and coming down for an afternoon is very encouraging. Sometimes I used to think from senior citizen I'm becoming senior, super senior citizen. But after seeing you all, I feel that we have long years to contribute. Thank you very much for that. How do I move this one? How do I move? Or you are going to move? Huh? You are going to move or I move? Okay, I can move it here also. Yeah, I can see it. Okay, so this is where we are located. Yes, I saw that. So we are located in Hyderabad. So the institution I come from, it's non-ferrous. There is no M. Material word is not there, but T is more important. Technology is a crucial word. In early 90s or late 80s and early 90s, Dr. Kalam and a few others, the Ministry of Mines, they said we have to create a new tech center, not a laboratory, but a tech center. The difference is that the technology center will operate at much higher readiness levels and bring things to industrial commercialization, production. And just before that, up to that level, it will work, TRL 8 or 7. And it will be product oriented. And manufacturing processes will be optimized to get a technology chain or a technology. I mean, technology produces a product. I mean, that's the first definition. Now, we had to create a knowledge enterprise. And what here, if you look at it, knowledge creation is science. Knowledge integration is technology. We have to take many multiple domain sets to bring in a technology. Even if you try to take a pencil, just a carbon lead is not sufficient. We need the wood, we need the materials, we need the binder, we need so many things, and even a printer on top of it to print the name. So in other words, many domains have to come together. So that's the difference between a conventional laboratory and a tech center that has to produce a product. So that was not there, and that is why they had to conceive it and create it. And I was a young man returning to India, and they said, "Can you think of working here?" Well, there is nothing yet, right? And if you consider that thing, you have a disadvantage and an advantage. If you have nothing and you're going to start from zero, then you can give it a shape, and form follows function. You can give it the right form for the function. The next thing is the what we call as we can bring in new rules, regulations compared to other existing entities, which is not possible if you are already trying to make a elephant dance to a new tune. You can't make it. So we said if you can have different rules and regulations only if you don't take money from government. So money giver gives you the rules. This is what Dr. Kalam gave the first advice. Normal. You take government of India from consolidated budget every year, you have to follow that. But if you are able to earn yourself, then customer gives you the rules. And if customer wants it yesterday, they will even be ready to pay you more. But they would expect a higher level of maturity in your output. Not you can't do some 100 grams and then say we have done the technology, you take it, right? So that's not it. So what is that we are in a big transition now. So on the left hand side, what you see is your base metals, as we call it, where one metal extraction from a predominantly rich ore has been the guiding force. And this is what happens, where 100,000 tons to a millions of tons is what is extracted. Iron, aluminum, copper, lead, zinc, tin. Silicon and manganese also. But the application which was driving it was structural, energy, transmission, production, and transportation. Steel was the workhorse. Whereas if you go to the right-hand side, we used to call them as technology metals. Now, the minerals for it are not predominant, except for a few. They will co-occur as secondary in the primary base metal circuit. If you have in a copper circuit, molybdenum, arsenic, antimony, so many other things co-occur with it. And if you don't take it out, you have lost it forever. It goes to tailings or slag or whatever residue it is. And it is more energy intensive to extract. And it goes into too many products, and you can't get it back that easily in a recycling mode because the entropy has become very high. For example, our cell phone has 24 of metals on the right hand side. So it's not easy. Phosphor, very small amount will be there, milligrams on the screen. How many screens can you break it to take it back? This is the issue. So it goes to electronics, automotive, aeronautical, defense, energy devices, etc. So you can see the characteristics are very different. Now I'll actually go into the metals on the right hand side. Now you see the first line that is there. I have deliberately made the first line like that as a group. There are no special ores for it, no special minerals occurring predominantly as a rich source. Maybe for molybdenum, you might see molybdenite there, but you won't see bulk of it. Vanadium might come as titaniferous, vanadiferous along with this thing. But it will always be secondary, and it will come as secondary in the primary circuit. That means Molybdenum will be in copper, tellurium, selenium, arsenic, big copper, germanium, cadmium is all in zinc, gallium, vanadium is in aluminum circuit. So in other words, we should have done multi-metal extraction and we should have developed strategies and technologies for it, and we didn't do it. The next line we are a little better: titanium, zirconium, hafnium. There are ores. We are luckily our beach sands are there, but nickel, cobalt, we don't have anything. That's why I put it in red. Right. Niobium, tantalum, tungsten, deliberately grouped. High temperature, above 2500 Kelvin. And hydrogen reduction is the last step. So you have to consider three of them together. And tungsten has become very important because now after rare earth, China has closed the tap for tungsten. Chromium, silicon, because of your steel industry, it comes. Of course, the whole line of rare earths, boron, beryllium. The last line is an interesting line. They are called reductant metals. For a metallurgist, this is the set that is available to extract all other metals. And even this are, most of it are by electrolysis. So it's finally electrons. And electrons come only basically from carbon or whatever source of electrical energy. So we are back to carbon in a very big way. So we have to understand that. Means when you put a plant for that, you have to put a plant for the bottom one also. That is what people forget. And you don't have a calcium plant, but I'll say I'll do reduce by calcium, then you start importing calcium, right? So that holistic picture is required. So here is another slide I have made where you start mapping it. Now, what I have done here, basically, you can see the red, blue, green mapping. Red means we simply don't have it. Green, we have, blue, we can get something, right? There are 16 sectors like this. And if you look at aeronautical, aerospace, that is where the toughest ones are there, including platinum group, except titanium and rare earth, not available. Maybe now we can just manage. Nuclear, they have made sure that everything we can take out ourselves. Not bad. Automotive, yes, RE magnets we can make now, but lithium, nickel, like that you can go on and on and on and on. So the important message that I'm trying to convey here is, whatever we do, we have to map it to sectors and see. And if that sector has to develop, all of these things has to be made available in the supply chain. And if there is a disruption, that sector will get hit very badly. Let us take, for example, cutting tools for manufacturing sector. Yes, tungsten carbide, tungsten, all these things are whatever it is. And if it is not there, we are gone. We still don't have molybdenum for high temperature furnaces. We are importing. Then pharmaceuticals. And one more thing is fertilizer. I put it in big red there, Fertilizer, potash is too very important. We have signed something with Canada, and one of the companies, Indian companies, is setting up a joint venture there with Saskatchewan. So in other words, a holistic picture is required when we look at minerals and metals. And we always have to do the back. From the sector, we have to see where we are going to get, and we need a solution path. So in other words, if you do a roadmap and a solution, we start with the sector and try to do it. This is what I brought in. Now, what is the knowledge that is required to separate? These are all called separation processes. All of it is known. It is how many years? 200 years plus this area of separation process people have been working on. So you will not have problem of knowledge. But what I've done here is, I try to bring everything in one slide. The first two lines are mineral beneficiation. Many of you know it already. The one that is the roasting and leaching, all possible things with which we can leach. I put it down. For example, ammonium sulfate. Today we use ammonium sulfate for taking out REs from any body, whatever, clay or ionic clay or even hard rock. After you have beneficiated it, you have to take it out. We use ammonium sulfate. The sulfate is not just sulfuric acid, but even ammonium sulfate. That means you have to produce a lot of ammonium sulfate also as a co-chemical in the plant. OCl minus is our bleaching liquor. Sodium hypochlorite. These are hypochlorites, right? So in other words, all of these things, ammoniacal or Caustic soda, of course, aluminum industry has it a lot. So in other words, all of these things, if you are getting it from a lower and lower tenor as a byproduct, you can imagine the consumption that we have to handle. So we need something very intelligent that we have to do. Like that, we come and we have to take it out selectively with solvent extraction, ion exchange. We need innovations in that. What I have put in red is all high temperature. So we need slag metal equilibria or for pyro with air, inert gas, hydrogen, vacuum. Because once we are in these specialty materials, vacuum processing and hydrogen-based processing become important. In other words, core competence in this many things is required for development of technology. So in other words, if I have an entity which can handle all of this, then I should be able to take any starting feedstock and try to get a solution for it. So this is how we approached it, and I gave this to PMO as a methodology. Now, what is our challenge today? Our challenge is, yes, we need to reduce chemicals, energy, and water stress. That's our challenge, right? In other words, we have to return the water as much as possible. We can't just take rivers and streams and use it in hydrometallurgical plants. We need to have a robust plant which can take inputs or feedstock from primary, secondary, scrap, recycling, everything. We cannot be one feedstock based. We should be able to bring it to an intermediate level with a pre-treatment and then carry on. So the way in which you do a new plant today or diversify or even modify an existing plant, we should be able to take multiple feeds. We need zero discharge and closed loop. So our problem is not only that. Our problem is you're going to put in energy, right? But if you're taking out very less out, what are you going to do with the rest of it? You're taking, let's say, gold. I took gold about 1 ppm from Kolar gold mine tailings and 1 ppm of palladium and rhodium we discovered. But 1 ppm is nothing, 1 gram per ton. Still the ton is remaining there. So we have to find byproduct. And you can see red mud too, everything, at least fly ash has started getting evacuated. So we need that solution. So we will come to rare earth as a case study, because I think today only they have rolled out the RFQ for for PLI scheme, I think. So what we found out is that we did a SWOT analysis first. Process knowledge is known. We can reach pilot plant fast. That much. That means capability of knowledge, or capability and knowledge holding is available. Raw materials is available for us in India in beach sands, monazite residue. Prior work in critical sectors like strategic sector is available as a nucleus for a lot of them. Small disjointed work all over the country. Lithium-based plants using used batteries is operational. Some people have come. We have started putting a first RE1 as early as 24, and now by 25, 26 it is. But what is a weakness? We don't have domestic raw materials. We have a bad habit of working in a serial mode from lab to plant. So we said we have to work ulta. Start with the plant and see the gaps that you have to fill. I'll elaborate on this, what is called adaptive walk. Therefore, we need a mission mode. Okay, if you have this, what is the opportunity we have? Can we do in 24 to 36 months, 500 tons, 200 tons, metals of at least 6 important metals we take, and then we do. But we don't wait for new blocks to come ready, and it'll take long time. But can we start with whatever available raw material from anywhere in the world, but start the plant and size the plant so that we can scale it up later as multiple modules. This was one strategy we gave as a tactic. Then one more thing I've written in blue, which is specialty chemicals. All of you are working in this area know that all these beneficiation chemicals, solvent extraction chemicals, ion exchange resins, everything is imported, right? What stopped us from developing them? Just one chemical can become a startup, can become very big, right? So what do we need? We need a higher separation ratio in new chemicals. So we said we'll start a lot of R&D on it, and last 3 years we did it, and we have come up with something. So the footprint of the plant will come down. if you are able to get new chemicals which can separate better. Of course, funding, we got it. What is more important, which I've underlined, is concurrent engineering. That means you don't wait for something to finish, go in serial mode. In big problem in India, when even when you see this thing, I used to say God will give the boon, priest won't deliver it. Right? So PM level to all the people will say, this is important, do it, whatever we want, we'll give you. But by the time we put a proposal, this, etc., committees will come, that will come. First question they will ask is, what is the scale you have done before? What have you done before? Etc., etc. Oh, this has to be done, no questions asked. We did not ask when a fighter aircraft has to be made, have you done the fighter aircraft before? We have to do the fighter aircraft. That's it. We have to do the missile. We have to do the submarine. That's it. There are no questions asked. So we are used to that training, right? So that's a mission mode. So you start from the output and work backwards. The same thought process is not there. That's what we are trying to bring. And again, robust processes to handle. What is our threat? We are already seeing it, disruptions, and one country can mess up everything. So we are saying that, okay, we start with whatever we have, and you can even start with secondary, primary, as well as even import, take assets abroad. That's what I've been encouraging people. So this is the, now let's come to the national scenario. What do we have? So we have, okay, in iron ore, bauxite, wheat sands. Everybody knows that. We have titanium rare earths. We have limited reserves in copper, zinc, lead, etc., etc. The red one is still red, and no reserves in cobalt, tungsten, etc., etc., and insignificant extraction from our primary circuit. So I said, why don't we encourage base metal producers to take out the secondaries, even if it is not viable, give them incentives to do the viability gap. Now let's come to the first step. In this set, you have to go to the primary metal circuit and then take it out. So we have to incentivize the primary metal producer, ask them to put a pilot plant, or I even went to the extent of saying, just put the plant there rather than somewhere else. I mean, you can't take out gallium from taking their liquor out and bringing it back. You can't do that, right? But gallium nitride is even more expensive than gold, and gold is at least is available. This is not available. So I mean, they say, different horses for different courses. Like that, for each metal, you need a strategy. So this is how it is. And if you know, throughout the world, molybdenum comes only from the copper circuit. Chile and Zambia, they produce because it co-occurs with it. And if they don't take it out, you will not have it. So that's what it is. Now, this set is very good, but the problem is this, that catch 22 came. They said, where is the market if we produce the metal? Can we do the investment? If it is very less, why can't we import it from China or USSR when it is cheaper? But when disruption came, they said, why did you not? Why have you not done it? So that is why I said this catch 22, we have to break it by distinguishing capability from capacity. Capability is non-negotiable. We have to have capability in everything. Capacity is a business decision, right? And from capability to capacity, we should estimate within 6 months, 1 year, whatever it is there, we should be able to go up. We should be ready. So this is an important roadmap solution strategy I gave. And I gave the example of titanium. We needed it for space and we needed it for so many things, but Atomic Energy kept it. They said it is cheaper, available from Soviet Union. Why do you want to spend hundreds of crores and put up the plant? But when it was not available, then what do you do? That's what has happened now. So the whole game was fought. So that catch 22 happens in decision making, and that is where the important concept of capability versus capacity decision has to be taken. See, if we had not kept the rare earth magnet knowledge and capability alive in a pilot plant, today we can't scale it up. We can't start from zero. And that is where it is important. So this set is the most important set. I'm telling you here, any company, anybody who has access to this as a mineral or as a anywhere it comes, because this has the largest impact next to REs on all our sectors. Aerospace, without nickel, cobalt, titanium, this set, We can't do anything. So I said, we will even, I'm taking tin tailings, tin concentrates, whatever is available, but I'm not able to clear it in my customs container load. This is the problem. In our country, policy is made, but operationalizing it at the lowest level, they say, sorry, even we haven't made even duty zero. But they say you can't bring it in because some clearance is required. It might contain a radioactive material. I said, let it contain. We will analyze it. We will take it out, keep it aside. But we have to process it. So it's going in circles. So in other words, this is what I brought it to the attention of PM. I said, what is this? I mean, that's what I told, no? God will give the bone, priest won't deliver it. Right? So who will come and, without a supply chain raw material for 10 years, will a bank give loan to put up a plant? So these are the exact words I have to tell to the finance ministry. I say, I'm a third person. I'm not even a company. So there is no self-interest involved. And I said, this in China just takes it. So we have to follow China and Japan. Japan, what? They don't have any raw material. Like this, like the situation we have in this sit. They have knowledge in process technologies and plant building. So they bring raw materials from anywhere, including energy, and push out the finished products. A country of 80 to 100 million. China didn't have process technology for a long time, but they had raw materials. Now, moment they got the technology know-how, you see how powerful they have become. So wherever we have raw material, we have to follow China. Very fast we go to them. Wherever we don't have raw material, we follow Japan. So this is a sum and substance of it. And that's what I said. Whatever it is, they're important to this. Okay, so we started looking at all secondaries, all these things, and try to take out. In fact, I was telling Hindustan Copper, look at your molybdenum sitting in your concentrator ore. I know it was there 20 years ago, but Uranium Corporation also had it. Everybody closed the secondary circuit. Not viable, but today it is important. Now, set 4, we are good, and we need to set. But people say, no, I found RE here, RE there, and all that. There's a lot of noise. But we need to snatch order from chaos. REs of all the 17 is not useful. Lanthanum and cerium, if it is, will always be more not very useful. We have something called MREs, magnetic rare earths. There are 6 of them: NdPr, samarium, gadolinium, dysprosium, terbium. These 6 should be have a threshold, certain minimal quantity. Then it is viable, or we beneficiate it to this quantity. Now, the last set, reductants. Carbon, hydrogen, that's it. That's what, and electrons. These are the only 3 major reductant. And it so happens even electricity is produced from carbon. Hydrogen is also produced from methane or electrolysis. Again, electricity. Finally, we are back to carbon. We can't live without carbon. And that's what I mean, coal guys should be happy because finally we are a carbon planet. So what we have to do is that it's not that we take all the photosynthesis that has already happened and take it out, but we have to go back to photosynthesis, even in a synthetic way. At least we can produce electricity. That part of the carbon we can substitute from renewables. So this is what happens. If you have magnesium, you can produce titanium, zirconium, hafnium. If you have sodium, you produce niobium, tantalum. If you have calcium, you produce this. Like that, it goes on. Hydrogen is used to produce moly, tungsten, etc. And electrolysis is used for all of these things. So now this plant, whatever plant you think of, you need a plant for subsidiary plant or a secondary plant for the reductant also. In other words, you have to look at it little holistically. Okay, so what is the roadmap? So this being the scenario, okay, they said, okay, we can have 3 solution parts if we don't look at the primary asset. So urban mine, end of life products, secondary source, imported concentrates. So capability and capacity. The plant size can be anything, can be 100 tons, 10 tons. If you are doing gallium, even 100 kg per annum is a lot. You'll make more money than even making copper. Right? So in other words, we don't have to have a predisposed obsession with the plant size. You have for nickel, yes, 1,000 tons is right. But for niobium, even 100 tons is good. That means what? Many things can be just a pilot plant. What we think as a pilot plant in others is a full-fledged plant for critical metals. So your footprint, your size, etc., will be lower. So if you look at urban mine, these many things can come out of it. Okay, battery waste, people have already thought about it. The difference between battery waste and e-waste is e-waste 90% is plastic. In battery, 90% is valuable metals. Hard disk magnets, it will not come back. It will take 15, 20 years to come back. Used solar panels will start coming back, and it has a lot of silver. Now, silver being a commodity, Warren Buffett took out 25% of the world production of silver and put it in a vault, and that is why the silver prices went up. Deliberately engineered, right? And indium is very difficult without it. So all of those things will start coming from solar panels, which have to be recycled because we are going big way, and all the we are already 10 years into solar. So by 10, 15 years, the panels has to be decommissioned. So for each material, we need for each end of life of a product. Now we have to map it to the critical material. So we do the urban mine. So I was saying that every town, every city, every state should have an urban mine concept, right? Not a scrap yard, but an urban mine. I mean, you start segregating it, and there AI and all kinds of things can be used. If you look at it, this is where I was very seriously working on. I said, take assets abroad and start importing it. For this set, cobalt, nickel, tungsten, molybdenum, tantalum, the 6 plants that I'm putting up, apart from RE, I said we have to import. In other words, let us get it from Africa or South America, wherever it is available. We need to acquire, or we need a long-term offtake arrangement. But we can't be, at least we need, for our strategic sector, we have to run the plant here. So tin tailings, we're trying to take many, even lithium and nickel, cobalt, Kelly, we are looking at 1,000 tons capacity. Now here, why I want to distinguish very important what I call as strategic thinking. You can't think like a businessman all the time. You have to think strategically from the nation's point of view and security point of view. If you produce nickel sulfate and nickel chloride are better for coating purposes, for nickel plating baths. They command more price than nickel metal. Will anybody add an extra step and an extra line of electrolysis and produce nickel metal? That is what has happened. So in other words, business-wise, it makes more sense to make an intermediate product and push it out because that sector gets served well. But there is another sector that is getting hurt. So in other words, there we need a solution. Every metal, every sector, we have to microscopically look at it and look at it from the strategic security angle. For my aircraft engine, for so many other things, I need nickel as a metal, vacuum grade, as a powder. But nickel sulfate for coating baths, everybody in Bombay to everybody will pay more. And take palladium. Palladium chloride is more expensive than palladium. It is again used in coating industry. So who will make palladium? Right? You push it out as palladium. You are putting less palladium and getting more money out. So you need a mix match of those things. And all of those things, we need very efficient recycling. We can't leave it. Wherever we sell, we have to mark it whom we have sold to. So this is where the large data analytics that we have, whatever is sold, we'll know. Today, battery ke liye, we can do that one, like a passport. So whatever is sold with more critical materials content, we have to trace it and bring it back, make it mandatory to take it back. Right. So this is what it is. So this is a way in which. So take out all of these things and put it in one slide. What is the resource? X-axis is resource inputs. That is knowledge, facilities, finance. Y-axis is impact. So if you have X money, people, and facilities, where would you put the money and in it, right? You have to be careful choice, right? So I was asked this question. I said, look, all are important, but what is greed is doable. The resource that you have to put is not very big, medium, but you can get all your REs out. So that is how these PLI, REPM, centers of excellence, all these things have come. And what is on the right top is carbon canisters, next generation. Carbon is the most important engineering material. You can get it from gas, you can get it from graphite, you can get it from coal, many carbon sources you can get. Hydrogen, we don't have to even talk about it. Hydrogen is very important because that's the only thing that we have which is not geography dependent. It's neither like Middle East or like China. We are not into lithium battery or energy device stuck there, or oil and fossil fuel stuck here. This is totally technology based. Cost is little high, but technology based. Why? It is the ability to produce electricity at a cost effective price drives it. So we have a renewable option. And it comes from Panchabhutas finally: wind, air, water, and sun. You can't get it better than that. And hydrogen has three properties. It is a fuel, it is a carrier, it is also storage of energy. Any other energy, you can store it as hydrogen also. You can move it as a carrier, and you can combust it as a fuel. So this property is now getting exploited. That is why hydrogen mission, however tough and difficult, we have to go through it. But I was saying that whatever ways in which we can, that is why I put it there on the red there. Blue is what I've been talking about all along. We don't have it resources, but we have to put this one. What is on the left here is titanium, zirconium. All those things are easily doable, and effort is not very big. So now that you have this one, we can make different groups in India work on different things and simultaneously make things happen. And germanium, gallium, etc., very high purity is required. So the impact is also there, but resource input is also high. Now this is a very famous slide I made, which everybody liked in PMO. I said, if you start from a new find from geological survey or whatever it is, etc., how long it takes if there is a potentially good one, right? So it takes 5 to 7 years, and in between you'll have a go no go, abort also can happen. If we have aborted titanium, which had high percentage in our bead sand, you can imagine what will happen to that. But we have no choice for many things. So what I said was, we will start pilots for many things, and our pilot can be 100 tons, 1,000 tons, or whatever it is. And in 3 years' time, we tie up the raw material source and we get many of them under one roof, many plants under one roof. 2-3 metals under one roof should be possible too, because we don't have time. So we start doing concurrent engineering. We start designing the plant as well as do the R&D on this extraction simultaneously, because we know the processes if you have chosen the process. Okay, how do we do it? This is the NFTDC. Till now, what I've given you is our national scenario, our strengths, our weaknesses, where we can put our resources, money, and energy. And our lived example I'm trying to show you as a case study. So over the years, we have worked on many things. And because it is a technology center, we are not like CSIR labs or other labs. We work on multiple disciplines simultaneously. That means we need core strength in multiple engineering disciplines: materials, engineering, design, electronics, and control. Without it, you cannot come to the level of a plant. You have to design the product. Your equipment is a product. Your product is a product. Your test bed is a product. All these are products. So we need the ability to develop, big system size products, and you have to control it. So you need electronics and control. If you can do that, we can do for an aircraft or for an automotive or for a knee joint, for anything. This is like three genes. So you take a problem and you break it down into what are all the advanced materials that you need, sector by sector, product by product. You design it and you manufacture. And that is how we have been doing. And because we have been doing it for 2 decades plus, it automatically evolved as a COE. It's not that it was best out to us. We earned it over a long period of time. This is what it is. In 2008, we started the electric vehicles because motors required advanced materials and then design, electromagnetic designs. Batteries require materials and chemistry, and controller is mathematics. You're controlling it. So it's math, physics, chemistry in a very beautiful propulsion system. Energy devices and materials to energy devices is very well known. It's the game. And biomedical devices are very advanced materials. So materials to a device to a system. That graduation was what was important. So what is a mission mode? This is from the space technologies. Space people define missions. Mission means they say every mission has a particular system. It could be GSLV-3 or a PSLV or whatever it is, or it will do a particular. And then it has a performance. It has to go to this orbit. It has to put this payload. And all these things are written down. And to do that, you need a system and a structure. And that's what we figured out first. We started putting a special purpose vehicle. Because you can't, for everything, you need the form correctly for that system and that mission. Hydrogen mission, I can't do it with another mission, right? For hydrogen mission, whatever is required, correct for it, I have to do it, right? So it is not a project, it is not a division. At least, even if you make it as a division, you have to make it as a special purpose division. Because hydrogen compressors or safety requirements and so many other things are very different. And you can't take somebody who has worked with some in another area and then say it. But therefore, you have to know, you have to break the problem down and see it. And you have to have leadership and with a lot of project management capabilities in the term. Project management is the key. And this is what I learned from Kota Harinar, and I was Tejas aircraft project director. He started with 2 people in a room with one line: make a fighter aircraft. Design, develop multiple work centers in the country, competence development, capability development, get the prototype, test, then come to capacity. Now you tell, this is how it is. So in other words, why can't we follow that? Or it could be space, whatever it is, lunar mission, planetary missions, human space flights. Each one is a mission. And each mission has its own challenges, but it'll all have some core technologies which are common. So for example, if it is a human mission, also the payload is human capsule and the service module. That is the payload. The orbit is a particular lower level orbit. So that the payload is humans now. So the point is the service module has to give all these life support systems, etc., and all the safety ejections and whatnot. The human capsule module is human being with ability to live in a habitat. So we are reproducing the earth habitat there. So in other words, for every system, we start breaking it down to what is required. So that is what is the creative problem solving and innovation. So what we did was we took this approach, systems view of taking total view of everything of what is to be done, and put a mission mode for its execution. So now from roadmap, I'm coming to solutions. How do you implement a solution? So start with output as a demonstration commercial plan. Don't start with, I know this, last 10 years I have worked this. That is why I said, no, whatever proposal I give, they will ask a question, have you worked on it before? I said, I have worked on 200 things before, but this has to be done. And this requires these things to be put into place. You'll put into place. So in other words, cross-fertilization and all these things are required, but we have to know our output. So our output is not research. Our output is not even a one prototype. Output is a plant. If you give that as a... Now, if you take that output and break it down, sir, you tell me how much time I have, then I can... Yeah. Deconvolute it. Now you take that output and say, okay, to do that plant, what are the processes and the equipments that has to be done? Processes and the equipment gives you the manufacturing line. So you have to know which processes that you're going to use. You can't be arguing about it. We'll start deciding on the set of processes. What is important is the third line. Can we do parallel processing and concurrent engineering? If 40 things or 50 things or 100 things has to be done, how many of them you can run it in parallel? See, parallel computing we do to crush time, crush the space required memories. This computer science guys know it all the time. Their aim is crush more in less time, right? Concurrent engineering. The next line is an interesting thing which project management people talk about, but they talk about it slightly differently. TRL 7 is the pilot plant and technology readiness. Done. Next is commercial. You'll know the techno-economic data, sizing, everything you can do. And what we defined technology 7 is not volumetrically increasing it, but bringing multiple domains, TRL 3 problems that we have to solve, integrated, sigma of that. So the more and more you get into the granularity, break it down the problem 100 times, then you'll know this. Today, if this event is happening, you start writing down the number of activities that would have been happened in the background or even in the foreground. You'll feel that not less than 50 activities would have happened. We take it for granted because many of them get aggregated and we start mapping it to a person after some time. That means if we start mapping it to a person, means it is embedded and it is matured. But if the person leaves, it's gone, right? So in other words, this is where the knowledge lies. So we have what is called generics versus specifics. Generic means these are fundamental truths, like wisdom. It will be there in every system, every specific system. So if you're studying a specific system, you will get the generic. Like conservation of mass, can you just go away from it? It is conservation of mass, conservation of charge, conservation of information. So you have decided on a path, a solution to reach the plant. But suddenly in the middle of it, you are getting an innovation. Somebody does something. So we should try and plug and play it also. So that is what we call as adaptive walk versus a random jump. This is in critical path management. Now, what is adaptive walk? I have to go from here to the airport. Yes. The output is defined. The endpoint is defined. My endpoint is the plant. So my endpoint is conducting a wedding or marriage or whatever. Done. But you are trying a walk, how to reach it. So you are looking at what are all the processes, equipments, technologies, this, that, raw material. We try to kind of use all these things, juxtapose it and get a solution path. I said 3 steps forward, 1 step backward, whatever it is. All those things happen. But suddenly somebody comes up with an innovation in one of them, one of the TRL3s. It could be in a design, it could be in a process chemical, it could be instead of this chemical, we can use this, or instead of solvent extraction, we can use ion exchange, like that. So it could be all this, but we should be able to plug and play that. The path should be such that we can plug and play and not get stuck on. And that is possible in critical metals because your plant is not a medium pressure 1 million ton bauxite leaching. You can't touch it once you have made it. For example, you can easily see Japanese went and bought for $5,000 the patent for continuous casting and annealing of steel plates, patented by US Steel Bethlehem. US Steel did not adopt it, their own R&D output. Why? Because we have already put the big plant. So we can't put this. Whereas Japanese took it and they did only this because they were starting green. Right? And they became more efficient, cost effective, whatnot. And they were driven by their automotive sector only, sheet. So finally, when US Steel was struggling, the CEO asked, like, what did you do wrong? They said the problem is that once we have done a capex for a very big plant in one way, if you have not made it flexible enough, we can't adapt any innovation as a plug and play even in parts. So what does that mean? No, sir, it is 35 years is the life of the plant. Only after 35 years we will change. By that time, even 10 more changes would have come, right? So in other words, those are all the lessons. But in critical metals, we are dealing not in million tons or something, even 1,000 tons. We can modularly plug and play another one things, and we know where the innovation is going to come, chemicals or equipments or whatever it is. I'll give you a very small example. Can we add energy like microwave or sonication and improve the leaching kinetics? Right. So like that. So we should be open for that. Is why we came up with what we call as, I given you the reference, you can go and read it. Origin of Wealth, Complexity and Radical Remaking of Economics, 2006. Since I specialize in thermodynamics, there used to be a place called Santa Fe Institute, where top Nobel laureates of specialized disciplines, physics, mathematics, chemistry, mathematics, all these people used to get together. And economics also used to go. And economics are the useless fellows there, because they know only equilibrium, Adam Smith type, supply demand. When this increases, the other will respond, right? They cannot handle non-equilibrium, complicated complexity. Whereas physicists knew it, the cosmologists knew it, the particle guys knew it, chemists also know it. So what had happened was they were telling economists, guys, you learn to handle non-equilibrium stuff. What is non-equilibrium? Lot of randomness, lot of stochastics. From that, you'll have to find the signatures of events. Stock market, for example, all kinds of things like that. That non-linear effect you have to find out. Today we have Iran war or any supply. It gives you a non-linear effect across the whole system. That is what physicists and chemists and others have migrated to. If you have to do a spacecraft launch vehicle, we have to look at every negative fault tree analysis. We say, if this fails 10%, what will be the effect across? We have to start predicting some of these failure events. And we are very scared of these non-linear catastrophes, where it is death, and failure is not an option there. So I would recommend that, in this, for critical path management, in higher level project management, we use this. This has been my favorite. Now let me come to the last part of the talk, where I have to apply it to a specific case and show how we did it. So the present case is this. So again, we start on the SWOC. What is our problem? Our problem is RE resources. We have some domestic, but we need foreign assets also. What is our weakness? We have not done good flow sheets, process flow sheets, manufacturing flow sheets. We have not done equipment design and a commercial plant till date. We are still worried about our economic feasibility because of Chinese way of pricing things, deliberately pushing you out. But we have opportunities. We know how to build equipments. Some of us have done it, and we know processes. We have a nucleus of it. Identify the nuclei and go. Second thing is, we can develop quickly entry-level plant, which is entry-level plant. What I say is 500 tons or 1,000 tons. We decided on 500 tons as a first module. Then we have to de-risk the raw material supply chain. That's where we had a problem. Only IREL was given that. So we said the states had it. Andhra Pradesh, Kerala, Odisha, and Tamil Nadu had it. But it was under Atomic Minerals Act. So I told the PMO, Atomic Minerals, so what? Anybody should be able to do it. It is people's assets. Let us amend it. So even without amendment, we can do it. Let the states make a 51% SPV. We know how to do SPVs. Only the state can do it. Let state be 51%. State plus PSUs can be 51%, and you can bring in others. Fair enough. So they agreed. He said, without changing the act, I will do it. So that is how I formulated the rare earth mission corridors and RE corridors. And the first one to take it up was Kerala. So it got into the budget also. And then finance minister expanded it. So for other 3 states as well, because it was not under National Critical Minerals Mission. I said RE has to be a corridor, not hub. The reason is this: Gujarat Mineral Corporation did it from hard rock and whatnot, etc., etc. See, they are already a public listed company, so any talk of critical minerals, RE will only push up their stocks immediately, right? All those things are possible. But here we are talking with raw material on the surface, right? So we don't have to even worry about listing, stock prices, all those things. He said from day one we can go. All I told is states do it. So AP and Kerala has taken it up, and I'm advising them, and I'm also uh, putting an SPV into it. We are very good in SPVs uh, because all the catch-22s we will cut with that. And so we do concurrent engine. So I told 2 external assets and 1 indigenous asset we should have. So I'm advising companies also, please don't just depend on whatever is available in India, keep 2 more. We are always used to 3 quotations, right? At least have 3 raw material supply chain if we can do it. Challenges, yes, we need to work end to end for viability. The first stage is very viable, last stage is very viable. That means from your ore or concentrate to a mixed oxide or a separated oxide, you make a lot of money. If you finish the magnet, you make money. But in between metal and you are losing money. But raw material oxide domestic price is very high because IREL has tied it up with Shanghai price. So even though I have resources, domestic resources in India, I'm not getting the advantage of it. Outsiders are getting the advantage of it because the way we have structured its extraction and companies and whatnot. That is why I said form follows function. So what is the best way? The one who has to make the magnet or other things should themselves have the resource. You can't buy. Even if IREL expands it, it's not useful for you because it is going to be Shanghai price. With that price, we need to reduce it by 50%. They were not happy when I told him. I said, look, I have to put up a plant means I have to convince bankers, I have to convince everybody else, boards and whatnot. And first thing they ask in the DPR is your raw material cost is high. What are you going to do? So then they asked the next question, how much it should come down? So I said it should come down by 40% on capex and 50% on opex. And 80% of my opex is raw material. So if I don't solve the problem, all my talk about natural resources available in India where I don't have a solution. So in other words, we have messed up with our own policies. Even when nature has given us a resource, we are messing it up. We have the ilmenite 4th largest reserves in the world. We are exporting ilmenite, importing titanium oxide for pigment. Billions of dollars we are exporting. We are not even having 10 to 20% we are not producing of what we are consuming. Iron ore we are exporting, importing, all specialty steels. So in other words, what is wrong? See, this is where we don't, here we have to think like China, blitzscale it. And where we don't have anything, think like Japan. Get it from wherever you are and powerhouse the technology part of it. So we have to address all the process gaps in the flow sheet with a high TRL, do all critical equipments and design it and render the plant. That way you reduce the capex and opex, you have to reduce it with your own in-house production. This was the mantra I've been giving for the last 2 years to everybody. I said, if you want to get into this, you do this. Okay, now our solution is this. We will make the equipments and go to at least, another question that is asked is, what should be the size of our plant? So there are 3 risks. One is your raw material, you have to de-risk it. Okay, our states and our companies can do that. The second thing is plant and machinery process know-how. We can help out there. Third is what should be the scale so that we are competitive with China, right? At a smaller scale, we may not be, right? So what should be the minimum? So I said 2,000 to 5,000 you have to go. Tons per annum. So then what happens is you have to bring in all of these things and start getting a plant out as so the target is reduce my input cost of raw material by 50%, reduce the capex, go for that scale of 2,000 to 5,000. Now you can see all of these things in the PLI now. But unfortunately, they said 1,200 tons max. They started with only 2,000 tons. So this is how it came about. So I'm asking many companies to come. So if you look at the process line, as I told you, 20 years ago, I started this and we had the line. At that time, even a pilot of 10 tons per annum was sufficient. We have to have separation from monazite residue or whatever hard rock or ionic clay, then go for extraction of metal, then strip cast, then jet mill it, align it in a magnetic field press, sinter it in high vacuum furnaces, then coating it, and packaging is also very, because two magnets can come and hit and break itself. So this much has to be done. So we adopted a company, Midwest, and we said we will do that. And I asked them to go and get their own raw material source. So that's how they went to Sri Lanka and they took concessions there. And we are now at 500 tons to 1,000 tons now. Hopefully, we should go to higher levels. And we will also help other companies. Even Coal India has approached us. We will help other companies similarly. This is just to show an example that it's all not talk. There is real time. And I didn't want to waste time on land again. There are existing plant. You can see houses everywhere. Huh? This is supposed to be industrial estate. So houses have come nearby in the last 5 years. But anyway, that is the last plot. But this process are very clean, vacuum, hydrogen, and all that. So this is what we conceived, and that's the reality. Now it's ready. So like that, we'll start putting up. These many grades has to be made. It is not like one output like cathode copper or aluminum. We have to do a large number of them. These are all called the grades, and it contains heavy rare earths like dysprosium and neodymium. So here is an example of random jump innovation. How do you plug and play it? We are using 2.53% dysprosium. Can we reduce it to 0.5? For that, there is a process innovation done. Now that we can plug it in, towards the end of it, or the alloying element side, we reduce it and do by a diffusion process in the end, and we'll be able to plug and play for that product. So that right from the beginning, even you're conceiving a flow sheet, we have to understand that innovations are continuously happening in any of these threads. And any thread innovation happens, I should be able to bring it in. Okay, now having done the plant side of things, I said I have to go and attack the other side, feedstock. Right? So these two are green. Now let's go to the feedstock. So feedstock, what we said is, okay, we have to now increase the availability itself for the ore or the feed material. So what we did was, okay, let us go to South Africa, Zimbabwe, Burundi, Australia, Sri Lanka, Mongolia, South Africa, everywhere, Myanmar, ionic clay, everything we analyzed. We said, let's go there. We have got material from all of these places. And by 2030, if I want 10,000 tons of magnets, I need 3,000 tons of oxides. And this is what it is. So what do we do? I have to augment the supply chain. So can I look at something else? And what we are looking at is, what else will have it? What we are trying to say is that, look, KMML and AP minerals as residues. KMML as a titanium plant with a residue. And we have some other things like ore burdens, ionic clays, and even tin mine tailings, whatever, which will also have monazite as a residue. So phosphogypsums as a residue. So all the residues, either monazite or clay or anything else, we said we can't leave it. We'll start looking at it, blitz analyze it, understand it. So what I've written in green is the best secondary source is ionic clay and monazite residue. So monazite residue is not just beach sand, it is in all tin mines. How do you think Australia is suddenly producing in Linus? It is because their old tin mine, they have opened up the tailings. That's it. Residues and tailings. So that is what it is. So there is a tertiary source also, which is your magnets, which have seen the end of life, and even in process waste, because you are cutting, a lot of sludge will come in the factory itself. That itself you have to remove. Again, like the previous way, I put it in a map. The matrix is large scale availability of a source versus the tenor of the source. The best is, of course, our monazite residue from titanium plant or tin or whatever it is. Clay-based REEs, if it is having dysprosium, etc., ionic clays. Then 4 is very good, middle, which is tin slag tailings. It is very good because you'll get niobium also, tantalum also. The overall value goes up, you know. You can have a strategy. So I have started attacking that from Africa. Phosphogypsum is another one available, South Africa, Russia, etc. But it is very gummy, you know. You have to have fertilizer plant along with it. In fact, the fertilizer plant is the main plant, and the RE plant becomes a subsidiary plant. So this is what it is. So we gave a threshold, how much it should be there. Monocyte residue will have 25% monocyte. Clay based will have 150 ppm only, but we can upgrade to 2000 ppm. So important equipments we said equipment and the process, right? Then we'll have a plant. So we started working on that and we are there. So that is how we said multi-material, multi-feedstock salient features. We should now do that as a backward integration for our magnet plant. We can't put up something and cry later, no? Like the way we put up naphtha plant for power and then say naphtha is not available. You can't do that. You have to think of it on day one. So what we do when we are in a pilot scale, when you do alloys, we say at least 100 to 200 tons as output, we say. If it is tailing or something, we say at least 1000 kgs per batch we should be able to process. And equipment sizing is accordingly done. And we optimize a line of equipments and do the process quality. This is the strategy of implementation that we are up to. Well, I don't want you to bore you with that. We have a model. So I'll just give you a small thing. We just need only 4 steps. And each of the 4 steps, we have to tweak it for each feed. First is, can you do any concentration by any method? Physical, chemical, even whatever way, clay or area, whatever it is. As per that, we find it's only gravity, magnetic, electrostatic, and floating. This is all. This standard set of 4 equipments, we put it, you should be able to tweak it and upgrade it. So it can come from different source, different thing. But finally, when you digest it, you bring it to a bandwidth of grams per liter in a solution. And then you start separating it and you will get a output. So this is what we have put, what is called multi-separate. We're able to take multiple feedstocks, what you see on the left, and work with an ability to take out this many of them, I told you, metals out. For that, we are also developing some special chemicals as well as process equipment, which will become plug and play into the flow sheet. So this plug and play is not a theoretical concept. We need innovation in special chemicals. We need process equipment. Everything gravity separation is 1G, but I can put centrifugal force and make it 200G. Solvent extraction, I need an organic phase and a liquid phase. Why should my organic phase is expensive? So I need my volume less. Aqueous phase can be volume more. So how do I mix it? I can't be putting a mixer motor and all that thing. I need emulsifying systems. And emulsifying systems are very well known in cosmetics, pharmacology, food processing, etc. The technology is lying elsewhere. The innovations has to be brought to this. So we have to develop the equipment for IGs. And since we work with aircraft, we know how to make those equipments. Because only the aircraft shaft will rotate at very, very high RPMs. So in other words, those equipments we identified which are required for innovations and special. So we will overtake China. We will overtake Europe in this in 3 years. So then start with industry partner on day one and start looking at basic engineering package. You don't start in a serial mode, right? Because our plant is our starting point. And we can keep on doing this BEP 10 times, 20 times. Today, with so much of computational power, modeling, AI, whatnot, right? We can do wonders. So, these many metals should become a plant next 2 to 4 years. So, this is what I've done. Then, last 2 slides, I'll show you. I have to do some religious conversion in 2 states. The government has to be transformed a little bit. So, what we did was we put Kerala Rare Earth and Critical Minerals Mission Corridor, a dedicated mission directorate. We have brought it in, got a new SPV done, like our models. They're all hub and spoke, but we have made it even bigger than that. And existing work centers and long-term vision and strategy. And a lot of SMEs and MSCs for downstream value addition so that employment and economics. So we are asking for a goal of $1 billion economy in the next 5 years to be created. So what I've done is this: so mission corridor, mission directorate, tech center like NFTDC, an SPV, a company, and lot of incubation clusters across the state and the neighboring states. So this is the model. And what we do is that the SPV company is having this many KMML, Keltron, NFTDC, and few more industry partners. So we created the SPV with government holding 51%. So we can attempt and do anything we want. So AP is the next. Thank you.
Have you got any idea of starting anything in the West Bengal?
I don't know, some Bengali come to me and
I am from AMD since 1959, retired in 95. Now, I am hearing my very pet subject, REE, uranium, thorium. Now I want to tell you that last year I revisited Jaduguda mines after 30 years. Now we are 600 meter plus below. Ore value has come down, but this byproduct from this is economically uplifting us. And once I was heading CBTA, columbium, tantalum, and beryllium unit of AMD, mainly working in pegmatite belts of Bihar, Jharkhand, elsewhere. And also, we were searching for inland places, not only beach sand. Many places we are having inland places, paleo places associated with costly jewels or materials in Odisha, in Rajasthan, in Madhya Pradesh, many places. So what I want to tell you, that I am very glad that I am hearing this. But what I am finding is this: we are not opening up. We are still in the pilot stage at many places. We must open to the industry. Otherwise, everything will remain in this pilot stage. Acha, have you heard that allanite, highly refractory mineral allanite? It is storehouse of these rare earth materials, but it is very refractory, very difficult to tackle it. AMD is trying, but I don't think they are yet successful. So
the sad
please
thing is
look at
we are
that
not even
also.
taking out 100,000 tons of that is sitting
and
on the floor. Right?
Time is passing out, that I am finding. Things are changing. Now this world war is taking place not only for oil and gas. It is for these critical materials now, critical minerals. It is very important. So what I mean, time is passing up. We must be fast and involve large fund and give the products to the country at large, our beloved country. Thank you very much. I am very glad to hear you.
Thank you very much. That's the whole idea. We have to compress time. Was the whole purpose of my talk. We can't take 7 years. We have to do it in 3 years, and we have to go to the plant fast rather than trying to prove in stages, serial working. The point is that many times many things were kept under Atomic Energy Act and Atomic Energy. Their requirement was very small, and to take out uranium and thorium, they were handling titanium, zirconium, and other things also. So that is why zirconium, beryllium, niobium, all those things are fully satisfied for their requirement. But it is for nuclear sector, it is but for civil sector not. So you have to open it up, and the only way to open it up is where the state is there. We have to empower the state, and to empower the state, you have to give them structures, you have to give them forms, you have to give them money. You form an SPV in Kerala or Andhra Pradesh or Odisha, whatever it is. Once it is there, even central government will give the money. You need somebody there with a proper structure, vision, function to receive the money also.
May
So
I?
that is it.
Sorry. My question is about your potash. Potash, you wrote that it is nowhere is now being.
No, we are in short supply.
But what happened? There is one mineral, glauconite.
Yes.
That glauconite was twice in that auction list was advertised for, and there was no takers. Thing is that, but my surprise was, manifold when I found that many Indian companies are importing for glauconite. Whereas in India, there are no takers to take them for mining and processing,
Okay,
etc.
this is a loaded question, but do you want me to answer it?
Now, my question is not that. My question is perhaps many entrepreneurs who could have taken her, they are not properly versed with the mineral, what is its use and why. Many of they put sub-consultant, they may not be knowing about this glauconite. It could be like that. This is my assumption. Otherwise, why? And both the times there were no, whereas it is being imported.
It is same thing like ilmenite and titanium oxide pigment, right? I mean, it's, at least in ilmenite case, we are exporting and importing raw material. The problem is basically this. As I told you, nickel sulfate was a nickel. Anybody, Vedanta has taken over Nicomet, and they produce only, they don't want to produce metal because they make more money in the other one. So the point is this: business decisions are not strategic decisions. Strategic decisions are from the national security point of view, economic and other security point of view. So if you look at it, they are now trying to see where all potash is available, even in Canada or other places, and then try to get it. But the fertilizer industry is a very complicated one, wherein subsidies are more and structures or deformed structures are there. Structurally it is very, very bad system. Leakages are high.
May I interrupt? Actually, where I was in Chhattisgarh, I myself segregated this glauconite from sandstone. Myself, because for different purpose. That was for age dating of the sediment. Because potash are this half-life and all these things. And I have segregated many grains quite easily.
Thank you very much. So what I have done basically is this. I asked for a very separate potash mission. In fact, I said potash mission, just like RE mission, we have to have a potash mission. It looks not very, glamorous across the world, but it is important for us.
And my second question
so we will somehow push a potash this thing, but everybody needs a solution given like a ready laddu. Only then our people take it. So we need the process, we need to do the plant, existing plant or whatever it is. Then they'll say price is not good, bad, and then incentivization. So it becomes a double incentivization. One, to incentivize to produce it, and then again incentivize for the farmers to buy it with an offset of that fertilizer price in the agricultural sector. But so be it. I mean, we need to feed billion plus people. I mean, we have to do that. And
my second question is, there is one mica we find in Degana with tungsten deposit, wolframite. So the Degana is Degana is it's known as zinwaldite, mica. This contains lithium. This is a new find. I do not know elsewhere it is known or not. But they say that with roasting it for 800 degrees centigrade or so, lithium can be easily segregated. Whereas this cannot be done in case of lepidolite, moscovite, etc. But zinwaldite is a new breakthrough. To me, it appears like that.
So anything that is having a layered structure with intercalation, we can take it out.
I don't know.
Anything that is mineralized more, it is a
Now, this is the mica zinwaldite new we find in Degana, which was a abandoned mine. Now it has been again set for auctioning and all. This tungsten is there along with that. This mica, this is a new find that this mica also contains lithium, which is easily segregable. That is what I wanted to know, whether
yes, a lot of exploration things that have now been studied. All the large data analytics have been grouped. And now that is how some of these auctions are happening, because they have selected some of those sweet spots for auctions. The thing is that carbon tungsten in one, this tungsten in Degana was known long time ago, and Hindustan Zinc was asked to stockpile 1,000 tons of it for defense purposes before it was eventually disinvested to private sector. In fact, we were the decision makers for holding the tungsten. So yes, tungsten with carbon, graphite, and tungsten with in Degana are now known. There is one more is now known in Maharashtra. So three spots are now locked. They are not auctioned. They're given by nomination basis. That is number one. Second thing is that lithium is a little messy story, because even from brine, very low level, it is brought up. With see, if you are taking 4 or 5 metals together, you're economically viable or whatever it is. Otherwise, it becomes a little tough. But lithium, we don't have to see in another 3-4 years. Sodium sulfur, lithium sulfur will come. The quantity of lithium required will come down. Already, lithium compound prices have dropped because there is a disruption of technology available there.
So I have got one very layman's question that's maybe a little bit irrelevant here. What is the present status of our critical and rare earth elements extraction from the insect, plants, and the living world? From insects, from plants, and other rejections.
We have no idea, but what we know is that proteins and biomass is used as a way to extract, but I do not know whether they host the raw material, rare earths.
For this seleniums and type of things, which are exactly this, in that some people, they eat the silkworm in Northeast and all those tribes, they do not have certain disease, and that we heard that there is a requirement of this for some of the medicines and all. They get it extracted from
Absolutely
by silkworm, like that. This locust and this even some of these grasshoppers, their body gives some of these critical minerals. And even our potato and this tomato, they have got certain things. Now, when we have got some lithium deposits and other deposits in some of the area, that plants and things, because they absorb, and it goes, even tea, they are having some 0.7 to 0.07 to 0.2 per kg, gram per kg concentration, some of these elements. Now, I just wonder whether in our country, in this area, those aspects have been taken or not.
Well, what you're talking about is what is called phytoaccumulation. Phytohyperaccumulation. Near mine sites, you'll always have plants actually accumulate. I mean, our Karya Pata is actually accumulating iron, right? I mean, that is how we say it as iron, right? So it has hyperaccumulated iron. And so, yes, hyperaccumulation, we use it both ways. When the tenor is, when it is in a solution at micromoles per liter level, very low dilute level, we can use these plants itself to biosorb and accumulate, and then we take it out. But they are all for remediation, yes. But for extraction, it is very difficult. I mean, if you are already in micromoles per gram, that means you have to use a ton of material to get a gram of material. So it will be
That's
tough.
what exactly I wanted to know.
So micro
because,
GPL and MGPL are difficult to handle. We need to come to GPL level in a
So that's
solution.
exactly for the post-mining mindset restorations, whether our species selection could be, because there we know about that. That's why I was thinking that whether there is any such activities and research.
I tell you what we are to do. Basically, I keep advising this. Our in-house R&D of companies should be very strong. They have to look at problems of that company, even remediation, tailings, discharge, and then work in a focused way on it, rather than get everything from outside. You need a nucleus of a group inside, even to absorb the information from outside. But it is doable, and all I'm saying is start nucleating research groups inside the organizations. I mean, not only you'll be smarter to receive from whatever is available. South Africa or Brazil or even Canada or Australia, they have not done anything very big or great. They have nucleated, in-house R&D centers with a focus.
Dr. Balasubramanian,
I think we can close the
your
question answer
lecture
session,
is
sir.
excellent. You have a lot of information you have given, but I have worked in steel industry for 36 years, and I took some project. Like any project, if you want to get money or get some advantage from the management, you have to show techno-economic viable. Whether it is techno-economics has been done by your company for each and every material.
Hello, sir. This is what I mean as what I call a strategic versus capability versus capacity.
No, but then the industry will not support.
So wait a minute. Why don't you let me finish? Okay, sir. I have also worked for 35 years.
Yeah,
right?
that's right. You
And
are fantastic.
and we have to do for a fighter aircraft as well as for a cryo engine, right? So what I'm trying to say is that capability is non-negotiable. Okay. If the companies are not ready to do it, etc., fair enough. The government has to do it.
Yeah,
Somebody
exactly.
has to
You
do
are
it.
right. You are right.
It is non-negotiable. Where you locate it, in what SPV you locate it, and that is we are doing. That is what some of us are doing. Now, after everything is ready, techno-economics is shown, raw material is shown, market is shown, anybody will do it. Today, I don't think you
Sir,
need to convince anybody.
I think he has to catch a flight. I know the discussion is very, very interesting.
Thank
and
you.
have lots of questions that you can carry on during the lunch session. So thank you. Thank you for question and answers.
Thank you, sir. As a mark of gratitude, I would like to request President of MGMI to kindly present a memento to our guest speaker. Thank you, sir. Before conclusion of the event, I would like to request the Joint Secretary of MGMI, Sri Ajit Chaudhary, to deliver the vote of thanks.
Good afternoon, everyone. Respected dignitaries on the dais, distinguished guests, and dear members. It is my privilege to propose vote of thanks on this momentous occasion of 21st Foundation Day of MGMI. At the outset, I extend my heartfelt gratitude to our esteemed guest, Padma Shri Dr. Balasubramanian, whose gracious presence and inspiring words have truly enriched this celebration. Majority of our gathering is goal-oriented, and in past I had a privilege to interact with Bala sir, and he informed me at that point in time that he has developed a technology to extract rare earth metals from coal waste and overburden available in the mines. So it was a good thing for us that a coal can also contribute to the rare earth industry. I would also like to thank our President Shri Satish Jha sir for his constant guidance and support towards all our initiatives. I express my deep respect and gratitude to Professor S.P. Banerjee sir. At this stage also, like, he is continuously blessing our events and supporting all the initiatives. I take this opportunity to sincerely appreciate the gracious presence of our distinguished teammates, team from Coal India, our CVO sir, Tripathi sir, Vinay Ranjan sir, Director HR, Director Business Development, Shri Ashish sir, Mukesh sir, Director Marketing from Coal India. Your presence today has a great source of encouragement and motivation for all of us. I would also like to express our sincere gratitude to all our past presidents and esteemed members of Council. A very special thanks to our Honorary Secretary for his tireless effort and meticulous planning that made this event a grand success. I would also like to thank Ms. Sushri Sangita for effectively comparing the entire session. We also extend our appreciation to all those who have joined us virtually. Your participation, despite the distance, and it reflects your unwavering association with MGMI. Finally, I thank each and every member available here in the gathering for your continuous support, and this presence shows your commitment towards the association. Let us now move forward with renewed energy and commitment towards the growth of the excellence in MGMI. Thank you very much.
This concludes our formal program. We cordially invite you all to join us for a lunch. Thank you and have a wonderful afternoon ahead. Shall I help?
Yeah, this is yours.
Event tips.
No, you leave the whole thing. Yeah. Is it shutting down? Yeah, it's okay.
Dr. Bharat, I'm from IIT. Oh, yes. I have something, but there is no time, and I didn't want to take your time. May I have your mobile number?